morning friends. Today we are going to discuss about the working of a CARNOT engine. What are the cyclic process take place in CARNOT engine is the combination of the four reversible processes, the two isothermal and two adiabatic process. Already we discussed about what is the CARNOT engine and what are the cyclic process take place in CARNOT engine. Again, we repeat the definition of the CARNOT engine. A CARNOT engine is an engine which converts the heat energy into the mechanical energy. Right? But here, in CARNOT engine, a cyclic process occurs, and this cyclic process consisting of the two isothermal and two adiabatic reversible processes. So in short, it is a heat engine converting the heat energy into the mechanical energy with help of the cyclic process consisting of the two adiabatic and two isothermal reversible process. Clear this? Okay. Now we are interested what are the cyclic process take place in CARNOT engine is completed in four stages or the four steps. What are the name of these four steps and what are the equation for this each and every step? So the question is that show the four step of CARNOT engine in P versus V graph and write the equation of each step. That's important question for the 4 marks question. For a CARNOT engine, do the graph of P versus V and mention the each and every step and also add the equation for each step. So here what are the cyclic process take place in CARNOT engine is completed in 4 steps. First step is 1 to 2, second is 2 to 3, third step is 3 to 4 and 4 to 1 is the fourth step. So here during the first 2 steps, the gas is, that means the system is expand. First the isothermally, then adiabatically. While in next 2 steps 3 and 4, the working substance of the gas is compressed. First isothermally compression and then adiabatically compression take place. Right? Okay now. So the answer of this question, so the 4 step of CARNOT engine in P versus V graph and write the equation of each step. Write the equation of each step. Right? Okay. Therefore, there are the 4 reversible process occurs in CARNOT engine. One is the isothermal expansion, second is adiabatic expansion, third is isothermal compression, and fourth is adiabatic compression. The 4 reversible process take place in CARNOT engine are shown in the figure. The first process is isothermal expansion, second is adiabatic expansion, third is isothermal compression, and fourth is adiabatic compression. Clear this? Okay. A cyclic process in CARNOT engine is completed in 4 steps shown in the graph P versus V. Now the CARNOT engine is also working same as the heat engine, converting the heat energy into the mechanical energy. Also the cyclic process occurs in CARNOT engine and this cyclic process is completed in 4 steps. The 2 isothermal step and 2 adiabatic step. Right? Therefore, a cyclic process in CARNOT engine is completed in 4 steps as shown in the P versus V graph. Now the step 1. Here the working substance is going from state 1 to the state 2. How the state of a working substance is changed. So here in the answer of this question only you have to mention the step name and also the equation. The description is not compulsory, you have to add. But here the description is represent that how the working substance of the gas is isothermally or the adiabatically expand or compressed. For that purpose, the conducting bottom of a cylinder is brought in contact with heat, and the gas slowly expand isothermally from state P1 V1 T1 to the P2 V2 T1. Already we derived the equation for the isothermal process, and already we discussed about the construction of CARNOT engine. CARNOT engine is a piston cylinder arrangement. The wall of a cylinder are perfectly insulated while the bottom is conducting. While the piston is placed in a cylinder, it can move up and down without friction, and piston is also the insulated. Right? So here in first step, when the conducting bottom of a cylinder is placed in contact with the heat, so what's happened? The gas slowly expands isothermally. That means from the bottom, the heat is absorbed by the gas. So as a result, the gas is isothermally expand from the state P1 V1 T1 to the P2 V2 T1. So here the gas is expand. Therefore, the work done by the gas, and work done by the gas is given by this equation. So what is the work done during the isothermal process? W is equal to mu RT ln V2 upon V1. In our case, if the heat absorbed by the gas is Q1, then the work done by the gas is W1 is equal to Q1 is equal to mu RT1 ln V2 upon V1. Why here W is equal to Q? That means that whatever the heat is absorbed, that is totally converted into the mechanical work. Here the temperature is even constant because the isothermal process. Temperature is even constant, therefore the internal energy of a system does not change. So from first law of thermodynamics, Q is equal to U plus W, but the change in internal energy is 0, therefore W is equal to Q. And due to the result, we can write the work done by the gas during the isothermal expansion is W1 is equal to Q1 is equal to mu RT1 ln final volume to the initial volume V2 upon V1. Again we repeat it. The first step is there is the isothermal expansion. How the isothermal expansion of a gas takes place? If the conducting bottom of a cylinder is brought in contact with the heat, that is the cylinder is placed on a heat source. That is the initial state 1. So heat is absorbed by the gas is Q1, therefore cylinder is expanded and it reaches to the step 2. The conducting bottom of the cylinder is placed in contact with or brought in contact with heat. So heat is absorbed. As a result, the gas is isothermally expanded from step 1 P1 V1 T1 to the P2 V2 T1. P2 V2 T1. If the heat absorbed by the gas is Q1, therefore the work done by the gas W1 is equal to Q1 is equal to mu RT1 ln V2 minus V2 upon V1. Clear it? That is the first step. Now in second step, we bring the conducting bottom of a, or we place the conducting bottom of a cylinder in contact with insulated state. That is the insulated state. Piston is already in second step. So due to the earlier absorption of the heat, now the gas is expanded. Gas is expanded and reaches to the third step. But here the temperature is changed because the amount of the heat, exchange of the heat is 0, because the bottom of the cylinder is placed in on the insulated state, therefore the exchange of the heat does not take place. Q is equal to 0. But the temperature is seen, therefore there is a adiabatically expansion of a gas. Adiabatically expansion of a gas take place. Again, second step is from 2 to 3 is adiabatic expansion. Now, the cylinder placed on an insulated state and gas is adiabatically expand from the state P2 V2 T1 to the P3 V3 T2. The work done by the gas is, for adiabatic process, we already obtained the equation of the work done. W is equal to mu R T2 minus T1 upon gamma minus 1. Actually, there is the negative. But here, W2 is equal to mu R T1 minus T2 gamma minus 1. Completed. Again, the step 2 to 3. There is adiabatic expansion. Here, no exchange of the heat take place for the adiabatic process. Because we place the conducting bottom of a cylinder in contact with the insulated state. Therefore, the exchange of the heat is 0. And due to that result, this step is known as the adiabatic. But here, the gas will also expand, therefore adiabatic expansion. Okay now. Now the cylinder placed on an insulated state and gas is adiabatically expand the expand from step P2 V2 T1 to the P3 V3 T2. The work done by the gas is from the equation of work done during the adiabatic process, W2 is equal to mu R. Actually, this work done is negative. Minus mu R T2 minus T1 upon gamma minus 1. But to add on the positive, we can add the W2 is equal to mu R T1 minus T2 upon gamma minus 1. That is our second equation. Yay? Okay. Now third step. Gas is now going from third step to the fourth step. In third step, the pressure is P3, V3, temperature is T2. While in fourth step, P4, V4, T2. That means the temperature is remain constant. Therefore, this step is the isothermal. Here the volume is decreased, therefore the isothermal compression. Isothermal compression. Now step 3 is isothermal compression. How we obtain the isothermal compression? For that purpose, now the cylinder is brought in contact with the heat sink. That is the conducting bottom is placed where they in contact with the heat sink. So what's happened? So the gas releases the heat into the heat sink. Q2 amount of the heat is released. Initially, the gas is in third state. The working substance in third state. Now there is compressed and new state is fourth state of a gas. Because the working substance releases the heat Q2 in a heat sink. So here the temperature is remain constant, therefore there is the isothermal and volume is decreased, therefore the isothermal compression. Now the cylinder is brought in contact with a heat sink. So the gas is isothermally compressed from P3 V3 T2 to P4 V4 T2. If the heat released by the gas is Q2, therefore the work done on the gas in first and 2, the work done by the gas, now the work done on the gas. Work done on the gas is, what is the work done? W3 is equal to the exchange of the heat. Because there is the isothermal process. W3 is equal to Q2 is equal to minus mu RT2 ln V4 upon V3. Here the negative sign is present, there is the work done on the gas. There is the work done on the gas. To convert into positive, this ratio is inverted. Therefore, W3 is equal to Q2 is equal to mu RT2 ln V3 upon V4. Right? Again, the third step. Third step is isothermal compression. Now, the cylinder is brought in contact with a heat sink. So, the gas is isothermally compressed from state P3 V3 T2 to the P4 V4 T2. If during this compression, if the heat released by the gas is Q2, therefore the work done on the gas is W3 is equal to exchange of the heat Q2 is equal to minus mu RT2 ln V4 upon V3. Yes, we invert this ratio. Instead of the V4 upon V3, we can add the V3 upon V4, so it becomes the negative, therefore negative, negative, positive. Therefore, W3 is equal to Q2 is equal to mu RT2 ln V3 upon V4. V3 upon V4. Clear? Now the last step, step 4. To complete the Carnot cycle from 4 to 1. In fourth step, P4 V4 T2, and in first step P1 V1 T1. Now listen, the exchange of the heat does not take place only the temperature. Here the exchange of the heat does not take place, therefore this process is the adiabatic process. But the temperature is changed from T2 to T1. And volume is also compressed. Therefore, this process is known as the adiabatic compression. Adiabatic compression. Now in fourth step, again we brought there is the first step and there is the fourth. Now the cylinder is placed on again the insulated state. There is the insulated. So there is the no exchange of the heat take place between the gas and insulated state. But the gas is still compressed, and that is known as the adiabatic compression. Adiabatic compression. Okay, again, the cylinder is placed on an insulated state and the gas compressed adiabatically from step P4 V4 T2 to P1 V1 T1. Again, now the cylinder is brought in contact with the insulated state. The gas is compressed adiabatically from step P4 V4 T2 to step P1 V1 T1. The work done on a gas is W4 is equal to same as this. But here the work done on the gas, therefore minus. Here work done by the gas, therefore plus. So work done on the gas is W4 is equal to minus mu R. Initial temperature is T2, final is T1. Therefore mu R T2 minus T1 upon gamma minus 1. Yes, here we change this T1 instead of the T2. Therefore, again negative. This negative becomes positive. Therefore, mu R T1 minus T2 upon gamma minus 1. Again, the fourth step is the cylinder is placed on the insulated state and the gas compressed adiabatically from step P4 V4 T2 to the P1 V1 T1. The work done on the gas is W4 is equal to, for adiabatic process, the work done W is mu R T1 minus T2 upon gamma minus 1. But here, the work done on the gas, therefore negative. Negative sign mu R, initial temperature T2 minus final temperature T1 upon gamma minus 1. Now negative sign from the bracket is common. This negative, positive. therefore mu r into bracket T1 minus T2 upon gamma minus 1. Now listen, from equation 2 and 3, both equations are same. Here the W2 is equal to mu r T1 minus T2 upon gamma minus 1. Here also W4 mu is equal to mu r T1 minus T2 upon gamma minus 1. So keep in mind that in Carnot engine, the cyclic process is completed by the 4 reversible processes to isothermal to adiabatic process. The first step is isothermal expansion, and the work done for the isothermal expansion W1 is equal to Q1 mu r T1 ln V2 upon V1. Second step is the adiabatic expansion. During the adiabatic expansion, there is no exchange of the heat, but the temperature is same. Therefore, work done W2 is equal to mu r T1 minus T2 upon gamma minus 1. So, first two steps are the expansion. Now, the next two steps are compression. First, the isothermal compression, step 3. The work done W3 is equal to exchange of the heat Q2 is equal to minus mu r T2 ln V4 upon V3. So this is also written as W3 is equal to Q2. Instead of the negative, positive mu r T2 ln V3 upon V4. And step 4 is the adiabatic compression. During the adiabatic compression, the work done on the gas. During the compression, the work done on the gas, while during the expansion, work done by the gas. So here during the adiabatic compression, the work done on the gas is W4 is equal to minus mu r T2 upon T1, T2 minus T1 upon gamma minus 1. Here negative sign from the bracket is common, therefore mu r T1 minus T2 upon gamma minus 1. Here this figure is not important, only for your understanding how the isothermal expansion, adiabatic expansion and the compression, isothermal and adiabatic take place. And also keep in mind these 4 equations, 1, 2, 3, 4. These important equations are important to deal what is the work done in Carnot engine during the one cyclic process. Right? Now from this equation, the equation 4 and 2 are same. Right? Okay. So there is the 4th step in cyclic process of Carnot engine, and now we are going to deal the work done during the cyclic process of a Carnot engine.